All right, let's get on with it. Our presenter today is Mike Kolsky. Mike graduated with a chemical engineering degree from Michigan Tech University and joined Novaspect shortly thereafter. Over these 15 years in the process control industry, Mike has helped customers as project engineer, a site support specialist, and now a senior systems controls engineer. Besides the before-mentioned teaching of our college students, Mike helps our customers optimize their challenging control problems as well as assists our customers in diagnosing and troubleshooting their interactive loops. So welcome, Mike. Thanks again for being here and sharing your insights with us. I'm going to turn it over to you now.
Thank you, Robert. Welcome to part 2 of our loop tuning presentation. It's nice to have so many of you returning after part 1. Today, we get to put the ideas from the first session into action. Here's a quick roadmap of the topics I'd like to cover today. First, we'll briefly review the highlights of part 1. Then, most of our time today will be spent on a simulator demonstration of the methods we introduced last time. Along with the demo, we'll also work through some sample calculations with the tuning equations. And finally, I'll introduce a variation of the Lambda method that can be used to deliver very fast, very aggressive results under the right circumstances. This so-called near integrator method allows us to safely tune very aggressively and to complete the testing and tuning tasks quickly. In part 1, we developed a motivation for effective control and presented Lambda tuning as a tool that delivered stable, predictable results. If you missed part 1, or if you just want to go back and review, that presentation can be found on our website, www.novaspect.com, webcasts.html. This slide here, the highlights from session 1, this slide really is the summary slide from session 1. We presented the Lambda method as a tool that enables us to achieve stable, robust control, which responds at a speed we get to choose. You choose and control your tuning outcomes. The Lambda rules match your goals to the measured process dynamics. Another benefit is the math involved is simple and can be implemented quickly and confidently. One of the biggest benefits is it allows for the coordination of multiple control goals. And finally, the testing task also serves as an opportunity to identify and diagnose hardware and process problems so you can fix problems at their root. Thank you all. I got a lot of feedback, a lot of requests, a lot of questions after session 1. Thanks for all that feedback. By far, the most frequently asked question I got after session 1 was, can you please work through some examples from the fuel and air demonstration used in part 1? We'll actually spend a good chunk of our time doing just that today. The second question I got was, does the Lambda method support tuning the derivative term of a PID controller? Yes, it can. There is a place for derivative control, and there are variants of the Lambda method that can accommodate those tasks. However, the simpler proportional integral only models provide very good results for the vast majority of the real-world loops. In the interest of providing the biggest benefit to the broadest audience, I'm still going to stick to the proportional integral only today. Still no derivative. The third question was, do these tuning rules you presented apply to all types of PID algorithms? And my answer is almost, not quite. There are 3 main popular forms of PID control algorithms out there. Each one requires slightly different tuning. Most modern digital controllers today use what we call the standard form PID. You might also hear this referred to as the ideal, the non-interacting, or an ISA form PID controller. Go back to the 1970s or so. Most pneumatic controllers of the time and most first-generation digital controllers back then used the series PID algorithm. You might also hear series called classical or interacting. Now the difference between the standard and the series is in how the derivative term is handled. So if tuning a PI only controller, as we will in all the examples today, then standard and series become identical. The difference is just in the derivative. So with PI control, the rules I'm presenting here can be used for either standard or series and will work for almost all of you out there. The exception is something called the parallel PID. Bailey used to use the parallel. If you're tuning a Bailey controller or some other parallel PID algorithm, email me and I'll show you how to convert the tuning constants from today into something that'll work on your parallel controller. So as I said, we'll start with a demonstration today of how to tune self-regulating processes. We'll use my fuel and air ratio control example that I used to contrast different tuning methods last time. And I want to step through 3 different examples. In example 1, we're going to look on a simulator at a very idealized, very simple, perfect self-regulating loop. In example 2, we'll show how to use the testing method in a little bit more realistic fashion to identify hardware problems. And in example 3, we'll look at a simulation of the fuel loop. This will have a few complications added to the simulation to make it more real world and to give you a truer feel of how you might tune things in a real site. What I'm going to do today is step into a Delta V demonstration. I'm going to use the demonstration time to show methodology and show the process. I'm going to skip pretty quickly over the math. When the demonstration's done, then we'll come back to the slides and show some sample calculations with the math. So for these self-regulating processes, the first question is, what do we mean when we say self-regulating? That is, when I make a controller output change, that's my red trace here, I change my valve position up in a single step. When I did that, my measurement or process variable, that could be my flow, pressure, temperature, increases in response to that valve position change, but eventually settles out at a new steady state value. There are 3 things I need to learn about this process. When we say a loop's dynamics, these are the 3 things we're talking about. The first is dead time. After I changed my output here, a certain amount of time went by when nothing happened to my process at all. This time that elapsed is the dead time. The second thing I want to know is the time constant. Now, the time constant is the time it takes to get from the end of this dead time to 63% of the way to this eventual steady state value. Rather than measuring and calculating, trying to figure out where we need to figure out this 63% point, a much easier estimation and simplification is just to look at the time to steady state and divide that number by 4. The third variable I care about is how much does my process change in response to my output change. That's something I call process gain. For this much output change, I got this much PV change. If I divide my percent PV change by percent output change, that is my process gain. So let's step to our Delta V simulator and look at the demonstration. I want to start today, much like we did last time, and that is I want to start with a compare and contrast and show the alternative method, the old school, high gain, fast tuning, Ziegler-Nichols method. In my trace here, the red trace in the top third indicates my fuel flow. The blue trace in the middle is airflow. To a burner, I'm burning this fuel with this much air. And the yellow trace on the bottom is indicating my fuel to air ratio. That's what's most important to me. No matter what my firing rate is, no matter how things are changing, I want the right amount of air to burn this much fuel. Now, this isn't going to be a boiler control demonstration. It's not a burner demonstration. This is just a good generic example I could find on how to coordinate two different flow loops to work together. This could be two different reactants to your reactor. This could be two ingredients to a baking process. Anytime we have two flow loops, even if they have drastically different inherent dynamics, I want their automatic mode behavior to be well coordinated. Let's start with a small step up in firing rate. In my simulation here, this number I've got down in the corner is just simulated firing rate, which is setting the set point to both fuel and air. Let's step from 57% to 59%. It's kind of a good example of checking your entries before you hit enter. I just about hit 0.59% there, but I saw my mistake and corrected it. So here is a 2% set point change. You can see the white fuel set point increase a little bit here, the blue air set point increase a little bit there, and the fuel and air are both going up, meeting it. And we have a little bit of disturbance there. We didn't quite maintain our proper fuel to air ratio. Let's try a little bit bigger step up. Instead of a 2% change, let's make a 5% change. 59 plus 5 is 64. One of the things I want to point out about this uncoordinated, unplanned Ziegler-Nichols method is the bigger the change you make, or the more rapid change you make, the worse this problem down here in the ratio is going to become. We both, fuel and air, responded quickly to set point, but they didn't go to set point quickly. They kind of shot past set point quickly. And the problem is air got there much sooner than fuel, so my ratio is much worse. Continue that same example of bigger and bigger changes. Now, a 10% change rather than a 5% change. Let me highlight this red trace so you can see a little bit easier. You can see by design with Ziegler-Nichols tuning, these overshoots are about 50%. So this height is about 50% of the initial change. This dip is about 50% of that. Eventually we settle in, but at the expense of our ratio wasn't very good through this. And as you can probably predict, if we make an even bigger yet change, our ratio is going to be even worse yet. Step from 74, let's do a 20% change, all the way down to 54. And what we saw is a 50% error, at least a 40% error there in our fuel to air ratio. If this was a real burner in a real world, this might have flamed out and not even been online anymore. So we can do better than this. I'm showing that with one of the major popular alternatives to Lambda tuning, we have significant overshoot, no coordination of responses, and the bigger our need is, the worse our problems are. We can do better. So let's start with looking at the air loop and how do we tune that first. Just going to switch to a little bit different chart here. This is that same air loop. You can see the overshoots we've had during my last demonstration. In this trace, controller output, where I'm telling my valve to go, is this blue trace here, blue, cyan, whatever you want to call that. The white line is set point, the flow I want. And the yellow is my actual PV or measurement, the flow I'm really getting in response to these valve positions. So let's start. Let's close the fuel faceplate to get it out of the way, and we'll focus on air for now. Let's start by putting this in manual. Now again, this isn't a real process. We're not dialed into somebody's factory or to somebody's boiler. This is a simulator. I built this simulator intentionally to be perfect. We're looking at something with no disturbances, no noise, a perfectly responsive, perfectly linear, perfectly precise valve. And another simplification is all of my units are 0 to 100%. That's going to make our math a little bit easier. I'm going to do something here that I would not do in a real plant, and that is I'm going to make a single bump and calculate tuning parameters from that. I just want to show you how easy the math can be. Before I do, let me zoom in so we can get a finer view of what's going on here. Instead of a 15-minute picture looking at the whole 100% span, let's zoom in. Now all these tests can be done. You could do this with paper strip chart recorders and stopwatches and rulers. If you were tuning a pneumatic controller in one of your plants, you can still use the Lambda method to tune those older simple controllers. The thing is, if you have a nice charting tool like this, it makes life so much easier. At the click of a mouse, you can measure what your output, what your timestamp, and what your PV are. So I'm going to make a 3% change. We're at 38.6% valve output right now. Let's step up to 41.6. And there's my change. Now with my charting tool here, the first thing I can do is I can put my cursor right there and click my mouse, and I can see that at 10:21 and 42 seconds, I changed my valve output by 3%. But my PV didn't change right away. I didn't see a change in my flow until right here. Again, put my mouse there and click. 10:21 and 44 seconds. I have 2 seconds of dead time. So my first piece of dynamic information, what is my dead time? I found in just a handful of seconds. Now I sized my chart right off the graph here. Let's see. How about if we go back to 40% output so I can see my PV back on scale coming back in right here. We'll let that come to steady state. It'll only take a few seconds. Let's make a 3% step change down. Again, valve position change there. Flow starts to change here, 2 seconds of dead time. I can already tell my flow is leveling out, and it looks like it's going to come to a new steady state. It is the type of self-regulating model we talked about. The second thing I want to know is how long is this time constant? How long does it take to get from where I started to 63% of the way to the final value? Well, again, rather than trying to measure this and figure out where I need to put my mouse, a much easier, quicker, simpler way to do it is to just find the time that it takes to get about 98%. I'm not going to measure this. I'm just going to quickly eyeball and say, right here, it looks about to steady state. So I went from 23 and 14 seconds to 23 and 35 seconds. 21 seconds. 21 divided by 4 is about 5 seconds. My time constant is 5 seconds. So now I know my dead time is 2 seconds. My time constant is 5. And my final piece of information I need to know is gain. Again, I can put my mouse here and click and see the output here was 40%. The output here was 37. My output changed 3%. My PV here was 56. My PV here was 51.8. My PV changed by 4.2. 4.2 divided by 3, my process gain is 1.4. So even with my talking, even with my explaining, even with all these pauses, in less than a minute, we found all three pieces of process information we need to tune this loop. So now let's expand this chart back out so we can see the whole 15-minute window, the whole span. Again, I'll come back in the slides and I'll show how to do this math in samples that you can take home and work on your own. In the meantime, I'm choosing a Lambda time of 12 seconds. Now that follows my rules of it's more than 3 times greater than dead time. It's somewhere between 1 times and 3 times my time constant. And I'm going to put in the calculated tuning parameters. They just happen to be 0.26, and my reset time is my manual mode time constant. I measured that at 5. Remember, the 20 seconds divided by 4 was 5. We enter that and we're done. No calculation really even. So now let's double check my, see again, I didn't quite click on that value. 0.26 is my gain. That's what I want. A reset of 5. It's a pretty good example there of, always check your entries before you hit the mouse or hit the return button. Now if we put this loop in automatic mode, if I make a set point change, I told you I chose a Lambda time of 12 seconds. My time to the new steady state should be 4 times that, or 48 seconds. Let's see how predictable we are. First of all, we should get to that set point in a smooth fashion. It should look like that same first order self-regulating kind of shape. There shouldn't be any overshoot, and I predict that I'm going to get to set point in 48 seconds. So I started at 10:26 and 49. 48 seconds later is that 10:27, 37. So right there, right now, is when I predicted we'd be 98% of the way to new set point, and predictably we are. So we've tuned our perfect idealized air model in just a couple minutes and got the results that we chose, we selected. Now let's move on to the fuel model. Same kind of thing. Instead of tuning, before we tune this, I want to show how to use the Lambda process to diagnose the health of your plant. Now this is a simulator, so I can easily change the behavior of my valve, easily change the behavior of my process just with a few mouse clicks. It's a little harder than this in real life. I'm going to introduce some hysteresis in my valve. And by hysteresis, I mean sloppiness. We tell the valve to move, and there's something mechanically going on there. The valve body doesn't go to where we commanded it. I'm going to say the degree of that sloppiness is 3%. Now, you wouldn't do that intentionally to a valve, and you certainly can't do it by clicking a button in the simulator. But I just want to use the process to illustrate. Again, let's zoom in a little bit. Oh. I want to zoom in both the X and the Y axis here, so let me click this. I'll zoom in here. Look at a shorter time frame and a little bit better resolution on the valve. So with my fuel faceplate open, let's go to manual, like before. part of this I'll simplify because I know that the hysteresis is 3%. In the real world, you're discovering this. You're not proving it, you're discovering it. But we have some limited time here. What I would normally do is I would start out with maybe a 0.25% bump. So from 45% to 45.25. And believe it or not, on a well-designed, high-quality valve with a good positioner that's in good mechanical shape, I expect a 0.25% precision from my valves. If I move the valve or command the valve to move by a 0.25%, I expect to see a change in flow. And in my example here, I didn't. We'll go back to 45, and there's no change. Now, most likely what's happening is the actuator stem is moving, but there's sloppiness between the actuator and the valve. I see this most often in rotary valves as opposed to sliding stem valves. It can be a problem in either, but it happens more often in rotary valves, especially if the connection between the actuator and the valve is a bolted square shaft. Sometimes that square shaft gets a little worn out and turns into more of a bow tie shaped shaft. So when the actuator moves, the valve gets left behind until that sloppy worn out part gets worked through. Another place this can happen is in electric motor actuated valves. They have intentional hysteresis built into them, so the valves aren't constantly saying small open, small close, small open, small close. Sometimes if they're close enough, the electric actuators just choose to be good enough with close enough. But my next step is I would try a 0.5% change, and I would keep moving up and down with gradually bigger changes until I find how big of a change do I need to make before I affect my flow. Now in this case, anytime I changed direction, I was moving more open, more open, more open. Now I made a change that's more closed. Anytime I changed direction, in this example, if my change is less than 3%, I'm only working in that sloppy area. I'm not affecting my flow. But as soon as I get across that area, then I do see a change. Let me go back to 42% again and show you why this is a problem. Here we're at 42, and our flow is at 86. Let's make a 4% change to 46. If this was my only bump, if I didn't do all these things I've been doing for the last 3 minutes back here, my conclusion, my incorrect conclusion, is that the gain of this loop is 1/4. I made a 4% change in output, and I see a 1% change in flow. Well, that's not the true gain of this process. What really happened is I have a loop that has a gain of 1 and a sloppiness of 3. So now that I found out I've got this hysteresis or this sloppiness of 3%, now that I've made a change big enough to actually affect the flow rate, let's make another step in the same direction. And now I learn my true process gain. My 2% output change here is going to result, and I know it will result because it's my simulation, in a 2% flow change. My gain is 1. So let me talk just one more type of valve problem. We've been talking about hysteresis or sloppiness here. Another problem that's even more severe and more problematic to our tuning is stickiness. If there's so much friction that the actuator can't overcome the friction and can't move the valve body, we tell it to open a little bit more and nothing happens, and open a little bit more and nothing happens, and open a little bit more. Now the actuator's developed so much air pressure, now it does break free and makes a big jump all at once. The way to distinguish between sloppiness in this example And stickiness is if I were to make another increase in the same direction I had been traveling on a sticky valve after it broke free, it would be stuck again. And I'd go through that same stick, 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 all of a sudden slip behavior. If you find stickiness, that needs to be corrected right away. Sticky valve problems cannot be addressed with tuning. For the sloppy valve that I'm showing here, I think my rule of thumb is if it's 1% or less, I can live with it and tune around it, but I'd prefer better. If I found a valve like this simulated valve that had 3% slop, I would schedule that to be rebuilt, repaired, replaced at our next outage. So now, I told you if I found a valve with 3% slop, I'd fix it. That means taking it out of the pipe, taking it back to the shop, rebuilding it, doing what you need to do there, buying repair parts. In my simulator world, it's as simple as I just changed the number. It's fixed. Again, to add some more real-life reasonableness here, let's add a little bit of random noise. So what we have now is even though the valve position is constant, our measured flow is chattering a little bit. This could be interaction from another loop. It could be just noise of the turbulent way flow is measured. It's reasonable, it's normal to have a little bit of noise here. I just want to show you that it doesn't really compromise our tuning methodology. We can work with this anyway. The first thing I would do is when you're tuning, check your tuning parameters. Oftentimes, PV filtering is added to filter out and average the effect of this noise. I don't want to see the effects of my filtering. I want to learn the true dynamics of this loop. So the first thing I'll do for my test is make sure that the PV filtering is turned off. Now I'm ready to tune this slightly less idealized loop, just like we did the air loop. So in manual mode, I'm already there. Let's make a 3% change, 48% to 51%. Part of what I want you to see is we don't need a whole lot of math, especially if you have a nice charting tool like this. We can use just eyeball estimates and mouse clicks to quickly get our information. So like before, I can see right here, I commanded my valve to move, 10:37 and 26 seconds. Right here, by my eyeball estimate, I think that's where the dead time ended. We're kind of having to pick through the noise, and on average, where did this flat line end and this upward slope begin? 10:37 and 30 seconds. I'm estimating 3 seconds of dead time. Like we did before, my time constant is from here until just about steady state. Let's call that right there. That was 28 seconds. 28 seconds divided by 4 is 7 seconds. Let's use 7 seconds as our loop time constant. Now in this perfect simulator world, I know that the real time constant is 8 seconds, and by my quick and dirty estimation, I estimated 7 seconds. I'm not worried about that a bit. The fact that we're 7 versus 8 is just fine. The results will be perfectly predictable, perfectly stable. I'm worried about not putting in 40 when it should be 8, or not putting in 1 when it should be 8. The difference between, by this quick estimate, we got 7 or we got 8, it's not worth splitting hairs over. And finally, we need to know our gain. For this 3% output change, my PV changed from, well, I have to pick some place that looks kind of representative of the average here. Let's just click right there, partway between a peak and a valley. 92.6%, 1,000 standard cubic feet per hour to, oh, this looks about typical of the average. 96.8 and we have .2. Now what about that 4.2? Remember, our tuning parameters are all in terms of percent of scale. So this scale, this PV scale, our flow scale is not 0 to 100% the way air was. This is in actual engineering units, 0 to 175,000 standard cubic feet per hour. So my change there is 97, okay, is about 2.5%. I've got about a 2.5% change in flow for a 3% change in output. My process gain is slightly less than 1. So using these numbers that I quickly estimated, some of the lack of quickness here was just my talking. To actually get the data, I made one bump test. I click there, click there, click there, click there. I've got all the information I need in probably less than a minute for a flow loop. Now we put our numbers in. I'm calculating a gain of 0.485. And a reset time of 8 seconds, 7 seconds, 8 seconds. Let's go back to our overview. Put fuel in cascade. We'll open up our air faceplate again. We'll put it in cascade. Both loops in cascade, both responding to this set point. We'll let that come to steady state. And the important final conclusion here is when I change this. Remember how disastrous a 20% change was with the old tuning? How bad this ratio got? Well, before I do that, let me back up and show one thing. While I had these loops in manual and I was making all these tests, seeing my ratio is out of whack, this is something in a real world you're going to want to pay attention, communicate with the operators, make sure that your bump tests are still within acceptable ranges. You've got to be a little bit, actually you've got to be a lot more careful in a real plant than we were with this simulator here. But make small, reasonable changes. Get permission first. This can be lived with. You just have to know how large of a change you're allowed to make. Now we'll make our set point change. Let's make that big 20% change that rocked the boat so bad with the old tuning. What I expect is this, in spite of the imperfections here, the slight hysteresis on the valve, the slight noisiness of the measurement, even with those imperfections, our fuel-to-air ratio remained pretty darn good throughout, and 48 seconds later, as predicted, we came to set point. So I hope the technique and the method we just demonstrated there was helpful. I hope that clarified some things. I got a lot of questions about this after number one. Let's go back to the PowerPoint slides. We'll look at the same examples, but now we'll look at actually performing the calculations. We'll go through this quickly. Last time, a lot of people said seeing the equations on the screen for just a few seconds was too quick, it was hard to absorb. A lot of you called or emailed and asked for a copy of the slide deck so that you could review the math at your own time, at your own pace. Anybody who wants this, this one will be available too. Again, I just want to show we started out in manual, at steady state, right here I made a 3% output change. So there's my change in output. I measured my dead time at 2 seconds. I measured the time it took to get to almost flatlined at the new steady state. So there's my time to steady state. And for my 3% output change, I got a 4.2% PV change. Copy these dynamic results over to the next page. And we can put the numbers in the equations. Process gain is 4.2% flow change divided by 3% output change. It's 1.4. Our time constant is this total time to steady state. This starts after dead time is done. 20 seconds divided by 4 is 5 seconds. That's going to be our reset time. And our dead time, there's no calculation. It was just a direct measurement. It was 2 seconds. Now we choose Lambda. Our automatic mode time, it's time to steady state divided by 4. Choose that number at least 3 times greater than dead time, and typically somewhere between 1 and 3 times tau. Put those numbers in the equation, and we got a reset time of 5 seconds and a controller gain of 0.26. Again, if you want this math to work through these calculations on your own and verifying you're coming up to the same conclusions I am, send me an email. I'll shoot you the slide deck. All I'm really showing you here, there's no real sample calculations. I was just showing the bump tests that we did to learn about the valve sloppiness. Make sure that after you work out through the sloppiness, you make one additional bump in the same direction to learn the true process gain. Now in my fuel flow example, this is exactly the same process. You start with the bump. We know the size of our output change, 3%. Measure our dead time, again, just by a quick eyeball estimation from the chart. Measure our time to steady state, 32 seconds. Remember in our real life demo, it looked about like 28 seconds to me. Let's not split hairs over that small difference. And we got a 5.8 thousand standard cubic feet per hour change. This is one difference. Remember, this needs to be normalized to percent, and this loop is 0 to 175 MSCFH. So the only difference mathematically between the air example and the fuel example is I rescaled this change in PV to percent change PV. I got 3.3%, which is the number I'm going to use, rather than 5.8 standard cubic feet per hour. Process gain is 1.1. Time constant is 8 seconds. Dead time is 3 seconds. And here's the results page. I'm just going to quickly step beyond this and let those of you who want contact me for the slides, work through this on your own time. But my hope is all the pieces to practice this and put this together for yourself will be here for you. The last slide, I showed you this example. When I chose a lambda of 12 seconds, I took a step down and I showed you that the fuel to air ratio held good and we got there in a predictable amount of time. I'm just showing you a couple examples of a faster or slower choice of lambda. The consequence is the reset time never changes. It's always the manual mode time constant. All we change is the gain. Higher gains lead to faster responsiveness, a little bit less resilience when things go wrong, but faster response when things are going right. And actually you can see with the slow, we're even better at maintaining our ratio than we were with slight imperfection in the fast, but we're still plenty adequate. So that's really it for the self-regulating part. One of the things that's characteristic of integrating loops is that they can be very, very slow. we don't have time to do a full-fledged demonstration of integrating loops, but I do want to give you some sample calculations to work through. This is actually an area where I got a lot of questions. When I said change in slope divided by change in output, there's a lot of questions about specifically what I meant there. So this is an example of a tank level. We said a full tank is 1,200 gallons. Now this could be 0 to 10 feet is our tank. It could be 0 to 180 inches. It could be in gallons. It could be a lot of things. I just want to point out that when we're doing the math, we need to rescale to percentage scale and not use the engineering units directly. But as before, well, let me explain this tank a little bit more. This is a tank level where something else is controlling the flow of liquid in, and our controller output here at 35% is controlling the flow out. So if we increase our output, more flows out and the level goes in. If we decrease our output, less flows out and the level goes up. The first thing was calculate the slope. Just measure the level here and its timestamp, the level here and its timestamp, convert to percent of scale, and you'll see we changed 8% in 75 seconds. The reason I use seconds as my units rather than minutes is because delta V's reset time is in terms of seconds. As before, I make a bump change in my output, but I don't come to a new steady state. As long as more is going out than is going in, I continue to decrease at a constant slope that won't change until my valve position changes. I care about what my dead time is. 5 seconds after I changed my valve position, I finally saw my level begin to change. And then I calculate my new slope at the new valve position. Again, this is in percent units, not engineering units. I've got a negative sign in slope 2 because my slope is going downhill. This is the sample math page. I won't step through all of this other than say my first step is to calculate an integrating gain, change in slope divided by change in output. So you can take the numbers from this page, work through and see if you come up to the same numbers I did. And we have some simple math to take this dead time, this controller gain, and this lambda that you choose to give you a reset time of 35 seconds, a controller gain of 4.2. Now, I told you last time how to estimate the slowest safe lambda time possible. Today, I want to say 3 times dead time is the fastest reasonable lambda you can choose. That's how I arrived. My dead time was 5 seconds multiplied by 3. My lambda time is 15. And the reason I want to know how fast I can get is really the motivation for this last kind of advanced idea I wanted to show today. This idea is when we can take a very, very slow self-regulating process and tune it as if it was a very, very fast integrator. I told you last time, choose your lambda times very conservatively. Be slow. And the motivation for being slow and conservative was if we have a high frequency disturbance coming from somewhere else, a fast loop is going to magnify that. But what if our process is such that the process itself filters out and removes all that high frequency noise? A good example of this would be if you're trying to control product composition and that flow is going through a large blender or mixing tank, or if we're doing pressure control of a very large volume, or even many temperature controls. That big volume, that big capacity filters out all the high frequency noise. So we don't have to worry anymore about being conservative and not magnifying it. In this loop, it took over 10 minutes. I made my bump change on this self-regulator. It took over 10 minutes to get there. Now what that means is, first of all, I'm sitting here twiddling my thumb, wasting 10 minutes waiting for that. Second of all, I'm not confident that everything else in my process is going to stay constant for the duration of my test. What if I just did bump tests like I did on my level loop? At the very beginning of this slope here, this looks like it's going to behave like a level loop. When I increase my valve position, it looks like my flow, my pressure in this case, is going to increase at a constant slope up. I decreased it. It looks like it's going to decrease at a constant slope down. So what we can do is we can tune this with the integrating rules, the rules we would normally use for a tank level, and use that guideline I gave you here of choose a fast lambda time, 3 times your dead time. Now what that does for me, I don't have to wait for this 10-minute change. I can make a change in just a few seconds. I can see my slope. I can make a change down in just a few more seconds. I can see my slope down. I have enough information after 2 bumps and the integrating rules to very quickly make some tuning. If I had used the traditional conservative 3 times tau rule here, this loop would have a time constant of 10 minutes. It would take 40 minutes to come to steady state after a disturbance. With my integrating rules, my time constant is 15 seconds. I don't have a ratio anymore of automatic behavior to manual behavior is 3 times longer. I have it's 15 times faster. So the criteria is on loops that have very, very long time constants and very, very short dead times, you can use this technique of the integrating rules for a process that's really a self-regulator. Very fast control, no danger of magnifying fast noise. So in summary, part 1 here is just a restatement of last week's summary. My additional summary points now are practice. With practice, you're going to gain the ability to tune quickly, effectively, and confidently. And finally, some of the stuff, especially the last 4 or 5 slides here, there's a lot of information, a lot of advanced information in just a few minutes. Go ahead and feel free to contact us with any of your questions or tough tuning needs. So we're going to open up the floor now. If there are any questions, you can type the question into your webinar control panel. We'll do our best to answer them.
Wow, Mike. That was fantastic. I have seen Mike present on this topic a few times now, and ladies and gentlemen, that is not easy to pull off. Transferring that knowledge, teaching with a live demonstration, very, very impressive. Mike is now available for your questions. Please use the control panel and type in anything you want. You can see on the slide right here, Mike's team, Dana, Travis, Tom, and Kurt. Novaspect prides itself in local services, and so these guys are spread across the upper Midwest, available to help you with your challenging loop needs. We have a quiet audience out there today. So don't forget on your way out as you exit our webinar that we want your feedback. So please give us your comments on what we can do better, what we can do next time. It really helps us. And again, always check back at Novaspect.com. for this recording here, probably later on today, as well as future events. Let's see here.
Okay, we have a question here of what is a cascaded loop control system. The answer to that is, in all of our examples today, none of these were cascaded. These were the PID controller directly sent its output to a control valve. A cascaded situation is where one PID loop sends its output to be the set point of another cascade loop. The reason you'd want to do that, we often do level control loops cascading to flow controllers. The reason to do it is if there's anything that upsets or disturbs the flow loop can quickly take care of that problem proactively before it upsets the level control. One thing I'd like to point out is people very often say the cascade slave needs to be tuned 5 times faster than the cascade master. The Lambda method gives us an objective method for how to do that. That simply means cascade slave has a lambda time 1/5 of the cascade master. Another question here was, what software was Mike using for the simulator? I was actually using Delta V, our Emerson Delta V control system. It's normally something we use to control a plant. In this case, I used it for all my control, and I built my process models with function blocks. It was actually a pretty simple effort to do it. So I didn't have a control system plus a simulator. I used the control system itself to do both jobs. Got another question. Can I explain again how to differentiate between a sticky valve versus a valve with hysteresis? A valve with hysteresis, or a sloppy valve, as long as you keep moving in the same direction, I open more, open more, open more, as long as I make changes in the same direction, the valve moves smoothly and predictably. The problem with a hysteresis valve or a sloppy valve is when I change directions, I have to integrate across that sloppy zone first before anything changes. Now, by contrast, if I took a sticky valve, it would stick until I got my output high enough to overcome the friction and then release. Now if I make another change in that same direction, it would be stuck again. So that's, I guess, whether you see the problem when you change directions or when you see the problem in either direction is the differentiator between a sloppy valve and a sticky valve. There's a question here that says, when normalizing the process variable, what should be used for the maximum? I hope I'm understanding the question correctly. All I'm doing is switching the PV change from engineering units to percent of scale. So if I had a temperature measurement that was scaled to read 200 to 400 degrees, my total span is 200 degrees. If I see a change of 5 degrees, 5 degrees out of the 200 degree span is a 2.5% change. So I think the question is, the maximum should be the entire scale of your transmitter and control loop. So thanks for your attendance, everybody. Thanks for the questions. I love the interaction. Go ahead and email me if you'd like a copy of the slides, and thanks again for attending.
Okay, thanks, Mike. That will wrap it up for today. Thank you all for participating, and see you next time.
The organ